In today's lesson, we are going to be looking at graphical displays of data. And we've kind of looked at this a little bit before when we looked at the types of data. We're going to look at just the different ways that we can represent them and some of the kind of the trends or patterns that might occur when we do graph our data. This is still considered a one variable analysis, right? Because it's a way to analyze our one variable. We've looked at the measures of central tendency. We've looked at the different measures of spread, and now we're going to look more at the graphical part or the visual part of it rather than the numbers side of analyzing our data. So in warm up, the following graphs represents the data from Stats Canada used in previous activity, looking at the percentage of people that ranked healthcare good or excellent for each province and territory in the year 2000. Reflect on anything you notice or wonder with regards to one variable statistics learned so far. So again, this is the percentage of people that ranked healthcare good or excellent in each province. Looking at our box plot, we have a histogram for the different years. For the different provinces in the year 2000. Is there anything you notice or anything that you wonder? So again, it's more of a warm-up to get you thinking about the different graphs. So the first are histograms. And we've talked a bit about histograms before. They're used for continuous data. And we've mentioned continuous data before. There's no fixed set of variables. Right? There's technically an infinite number of data points. Usually it's things we measure. Right? And it's useful to keep in mind, or there's two useful things to keep in mind about the intervals or about the bucket size. Right? So if you're creating a histogram, is the interval size nice? Is it a nice size, or is the range of each interval nice? Can you read it nicely on the histogram, or is it hard to see where each interval starts and ends? And then do you have enough intervals represented on the histogram? So when we're dealing with intervals, you want to have a certain amount of intervals to adequately represent the data. Now, a good rule of thumb is 5 to 10 intervals. So those are 5 to 10 different ranges. So it might be, say, 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25. That might be one option. Again, depending on what the values are. Right? If our values aren't in any of those intervals, then obviously that wouldn't work. And again, the reason is because it allows us to get a good idea of what the shape is, and that's what we're going to look at next. If we have too few intervals, right, basically meaning our range is going to be quite large, then we might just have one big bar. If our range is too small, right, or if we have too many intervals, then that means that we might have all intervals containing one. Right? Similar to why if we used a bar graph for continuous data, it wouldn't really help us because everything would appear as almost the same amount. Right? If you look at different percentages, the probability of different places or different people or different things having the same percent, right, might be relatively low. So it might just look like a bar graph where every individual data point is at 1. So again, that's the same idea if we have intervals that are too small. Now, there are 4 specific types of shapes to look for that describe how the data is distributed. Right? So the way the graph looks with our data can help us describe what's happening. So one might be a uniform shape. Right? So a uniform shape, bar heights are all roughly the same. So if we look at our histogram for bus wait times, looking at the different ranges from 0 to 1, 1 to 2, and so on, all the way up to 15, we can see that the bar heights are all roughly the same. There doesn't seem to be that much difference. Yes, there's a little bit of fluctuation if we go up, but generally speaking, it's all roughly the same. The bars are really close. So basically here we would say each interval has an equal chance of being represented. We'll look at that more later in the next unit, but basically it's saying that there isn't one wait time that's favorable over the other. The mound or normal shape. So kind of talked about normal distribution in a previous lesson. This is similar to what we might find with a histogram. We might see a normal distribution or a normal shape where the most occurring interval is in the middle. The median is roughly the same as the mean, and the modal interval, the interval containing the most data, contains both the mean and the median, or the average and the median. So saying again, the middle, the central values tend to be the same. Right? So if we look at this histogram for CO2 released per year by coal plants in the millions, we can see that the majority are in this middle section here. Right? The majority fall in the middle. You have a few extreme ones on the high end, an extreme on the low end, right? But the majority of it is in the middle, which is similar to the normal distribution that we talked about previously when looking at percentiles. Bimodal shape. So bimodal shape is data that has two peaks. It usually means that two different groups are represented. Right? So what you might have to do, you might need to reanalyze by separating the groups. Right? You might need to separate or organize the data a little bit better and then reanalyze it separately. So for example, if I look at this histogram for batting averages for the Toronto Blue Jays in 2016, I can see that I have two peaks. Right? Clear, distinct peaks here. We have one peak where from 25 to 30%, we have about 9 batters, and from 0 to 5%, we have 8 batters, or batting averages. So we see a discrepancy, or we see that we have two peaks, or clearly two peaks here. So what two different groups might be represented, right? Well, if you think about it, the 25 to 30, that's good batting averages, but that's not out of the ordinary, right? On this team, like if they're a good hitting team. But 0 to 5%, that's extremely low to have quite that many people batting that average, right? Basically, they're hitting the ball 5% of the time, anywhere from 0 to 5%. So what two different groups could we have? Well, maybe we have rookies, right? People that only play 1 or 2 games. Maybe they didn't play at all, right? So they'd have a 0% batting average. Maybe they're pitchers, right? Before the rule got, or before they kind of, I think they still do it, but in some divisions, the pitcher hits, but they don't want to try to really swing and hit the ball because they don't want to injure their arm, because then they have to go back out and pitch the next inning. Right, so they would probably they tend to strike out. Right, so maybe we've included pitchers in our batting average, or the players with batting averages. Right, so we might want to remove pitchers because they're kind of a unique situation in terms of batting. So their values might kind of misconstrue our data. So we might want to remove them and analyze it again. Skewed shape. So skewed shape is pulled to one side of the range or the other. Right? So basically the data tends to be more on one side than the other. And there's two types. Positively or right skewed means the data is mostly on the left side, but the mean is higher than the median. So this is basically saying that we have most of the data on the left side, but there are extreme values on the right side, on the high end, you could say, that causes our mean to be pulled. Negatively or left skewed, data is mostly on the left side, but the mean is lower than the median. So this means that we have extreme low values that pull our mean down. Right, so the direction of the skew is the direction the average is being pulled. Right, you might think of it as either positively or right, maybe not skewed, but tailed. Right, negatively left or left tailed. So if I look at this data here, looking at the histogram for violent crimes from 1962 to 2016, we see that the majority of data tends to be over here. That's where the majority of data is, right? We have our peak obviously on this end, and that's where the majority of the data is over there. What we do see though with this data is that it peaks and then it kind of trails off. it dips and skews to the right, or to the left, sorry. So what that means, right, so that's the negatively or left tail. Our tail of our graph is more on the left, right? It means the data is mostly on this right side, but all of these low values here, those are affecting our mean. They're bringing the average down, right? So the middle value might be more over here because the majority of data tends to be closer to the right. But these low values are going to be pulling the mean or the average and make it lower than the mean or than the median. So if we kind of redraw this in just so we have an example. So this would be an example of a left skew. Box plots. We talked briefly about box plots in a previous lesson when we had to look at percentiles. Right, there's 6 points that are used to create a box plot. The minimum value, the Q1, which is the 25th percentile, the median, which is the 50th percentile, the middle value, Q3, which is the 75th percentile, the maximum value, and depending on what software you use, it might have outliers if present, which we've done before. So again, we go back to that kind of initial question from the warm-up. So this is an example of a box plot, and again, we've talked about them before, so we should be relatively familiar, right? The main points we've mentioned, we have our minimum, which is one of the whiskers. We have our maximum, which is the other whisker. Our Q1, which is the first part of the box. Our Q2, which is the second or the middle line. And our Q3, which is the other part of our box. And then any dots that we see tend to be outliers. Again, the other part, this box represents 50% of the data, or is our IQR, the range, right? So it kind of helps us see where the majority of our data is, or that middle 50%. Where's that median? Right? So we can see how things are skewed, how things are spread out, to help us kind of describe, again, what's happening. So with the box plots can help to confirm the distribution that may not be visible in histograms, right? So sometimes histograms might be a little bit harder to tell if it's a mound, if it's a uniform, if it's skewed left or right, depending on how much data we have. But sometimes the box plot can do a better job of visualizing that, right? Specifically when we're looking for the mound or normal and the skewed shapes. So if it's a mound or normal distribution, what we should look for in a box and whisker plot is that the box will be in the center, the whiskers will be roughly the same length, and the median is in the center of the box. If it's skewed, the box will be more on one side, so the majority of the data will be closer to the left or the right. One whisker is usually longer than the other, right, because we tend to have more extreme values away from our data, right? That's talking about the skewedness, right? If it's skewed left, we have the majority of our data on the right, but we have a lot of smaller variables, or smaller values, sorry, on the left side that pull the average down. On the flip side, if it's a negative or a right skewed or positively skewed, right, most of the data is on the left, and we have a lot of extreme values on the right, or small numbers of them that are going to pull the mean or kind of shift that average. The median may be also on one side of the box closer to the max or min value, right? So it might not be in the middle, depending on, right, because it should be closer to the middle of all the data. So if we have a lot of low or high values and it's skewed, then the median will probably tend to be pulled towards that direction. So for example, here we look at the same histogram that we looked at to represent a normal or mound distribution. Right, again, we can see that the box is in the middle of our number line or of our values. We can see that the whiskers tend to be roughly the same. Right, so we can see how these two kind of relate, how one would represent the how they would both represent the mound or normal. Not to say that the histogram, it's not easy to in this case, but depending on how much data you have, sometimes it might not be. Looking at the skewed, so the same histogram that we looked at, right? So we see that the majority of data is on this side, but we have, again, these small values over here that are going to be pulling our average down. So again, we can see that in our box and whisker plot or our box plot, because our box tends to be more on the left side, and then we have this longer whisker over here representing all those kind of extreme values that would pull our average down. So that's kind of, again, where we can kind of see the relationship between the two. So again, that's the main part of the box plot, is just to help us see the spread of data, see how it's distributed. Finally, conclusions, comparisons. So to compare related one variable data sets, it is helpful to look at both histograms together or combine the two box plots as a side-by-side box plot or a stacked box plot. Right? So if I want to make the comparison between two cities or 2 years in this case to see if there is kind of a change or to see if there's any comparison, is it similar or is it different, things like that. We might want to put the histogram side by side so we can kind of visually see if there's any difference. And then likewise, we might do the same thing with box plots, right? We might stack them to see the kind of comparison between the two, right? So we can see in year 2000, this would probably be more of a right skewed. The data tends to be more on the left side, but we do have some positive or high values that are pulling the average up. The year 2005, you might argue that it's a little bit more of a left skew, with the box being more on the right and we see a longer whisker on the left. You could argue that looking at it, if we look at now the visual, that it looks a little bit more like a normal or a mound shape, but we do still have these outliers that might be influencing some of that data. So again, but allows us to make a better comparison, right? We can see where the majority of data is in each year. So we could argue that in year 2005, the ranks or the percentages increased. You might say there's more of a range or more of a variability in 2005, right? Slightly larger box, longer whiskers, things like that. And we can talk about the fact that both still have two outliers, or each has an outlier. So the main thing from this lesson is just kind of looking at the different types of displays, more so in this case looking at the distribution, right? How does this or how do these graphs or graphical displays see the distribution of data? How can we use these to help us describe how the data is spread out? Right? Again, talking more about the mound, normal, bimodal, skewed shape, and then the box plots, because that can give us some information on the data itself that we might not see from our statistical values, right? We might see from the standard deviation that the data does vary. There is some variability because it's a high value, but we might not get a good sense of what that actually means until we look at it graphically. So there is a time and a place for these graphical representations. You might have heard the quote, "A picture is worth 1,000 words." Right, so that idea, these graphs do tell us a lot of information that sometimes just the single values or single statistics don't. So it is helpful to see where we can use them and what they can tell us.